So good morning, everyone. Yes, my name is Youzuo. First of all, I would like to thanks for the invitation from Web, actually giving me the opportunity sharing the latest and newest work from our team. My first time being on this great campus, beautiful, beautiful campus. So, let me just talking about the work. So for today, I will be telling you, how do we using machine learning, how do we using physics, wave physics particularly, and combine it together and solving for a computational wave imaging. So let's get started. All right, so this is the agenda for my talk. To begin with, I will give you a kind of a very high-level understanding about, why we are doing what we're doing, and then going through we call it pure data-driven models, meaning that, we don't really leverage in physics, but instead we're only looking at data. The core part of my talk is going to be the third section, which is more about, hey, how do we using the underlying wave physics, and together with the data set that is being available and solving for the wave imaging problems, and then I will give you some examples, how do we actually leverage the models for solving ultrasound tomography problems, and give you some takeaway in the end. All right, so this is a Chinese word puzzle. All right, just so you know, Chinese is very different. Obviously, I'm one of the Chinese immigrants, and Chinese is very different comparing to English. Chinese is more of a symbolic language system, while English is more of the alphabetic way. So what I mean by that, for Chinese words, they're usually meaning by components. Each one of the components have its own meaning, and you combine it together, you actually may have a different meanings here. So do we have any wild guess what does that really means here? There are two components here. All right. Very close, wave, yes. Okay, good guess. All right, for the left part of the words, it means flow of the liquids. So it was like water, right? The right side of that, this is the surface. So combine it together, it was like, the fluid of water, flow of the fluid through certain surface, and that becomes a wave. This is a kind of a, Asian Chinese word. So now we have much simplified Chinese, so we can talk about it at a time. But this is essentially what we're doing, right? We are using wave as a tool to understand about media properties. So there's a wide range of applications from, for instance, very low frequency seismic wave to understand about Earth's body to extremely high frequency like the ultrasonic wave to understand about mechanical properties of human tissues. So for my talk today, I'll be first starting from this side. Understand about the low frequency wave, using that as a data set to developing a whole bunch of methods, and then we will switch our gears to apply that to ultrasound imaging problems. Since we're talking about wave, obviously the governing physics here is wave equation. So this is acoustic wave equation. There are two variables that are most interesting to us, velocity or speed of a sound, kind of measuring how slow the wave is propagating in the media. And the other one is the waveform, right? The pressure response of the wave respect to the media. So the equation to the left-hand side, this is the so-called fault modeling, meaning that we try to understand about how does the wave propagating from the source all the way to the receiver by passing through the media. And what really interesting to us is actually the imaging, the inverse problems, or the tomography, depending on which community that you're coming from, but they essentially meaning the same thing. Meaning that we try to provide it with the waveform measurement and to infer or obtain the velocity map or the speed of a sound. Solving for the problem is not easy at all. It is a typical ear-post problem, and it is extremely nonlinear. So a few years ago, when I was still at Los Alamos National Lab, together with my mentor, we actually developed a physics-based method, which we call it modified total variation methods for solving FWI. And a couple of very interesting lessons that we learned. One, the problem itself is, like I said, very challenging and computationally demanding due to this nonlinearity, due to these gradient-based optimization methods. And the spatial resolution is usually very low due to the poor data coverage. But there's one upside, which is the high robustness and generalizations. So now the question that we keep asking ourselves is, are we going to be, keep doing the same thing, or are we going to be switching something different? So a few years ago, me and my students and our team, we started to look into machine learning. Right? This is kind of a summary of the effort that we're putting together with respect to application, model, and also the data solutions. So in the first row, we're basically looking at all different kind of wave imaging problems, ranging from geoscience imaging, medical imaging, imaging with uncertainty, portable imaging on the edge device, as well as some of the quantum imaging stuff. And then in the central panel, kind of telling you, where were we from, and where we are doing now. Models including fully supervised methods, unsupervised methods using physics models, self-supervised, semi-supervised, and also some of the latest and newest wave wave diffusion problems. And the bottom row here telling you, what kind of a data solution that we have. I mean, just like many other machine learning models, data is going to be the building blocks for all those machine learning tools. And thanks to the physics behind that, we can actually using simulation. That is the work that's been done like several years ago. And then we're also looking at, how do we using nature image to help with the pre-training to generative AI and some of the latest newest work regarding using the open data set. So my talk today will be mostly focused on the model development. I would go through a couple of most recent models that we developed and kind of give you a flavor and how do we actually solving for wave imaging problems. So like I mentioned, for the physics method, they are obviously facing some serious challenges. The first one, like I said, is very expensive solver, and the accuracy due to the apoptosis itself is not high enough to capture some of the tiny features, but the generalization ability is usually good. So this essentially becomes the expectations when we're dealing with machine learning to see how machine learning could hopefully alleviate or maybe even overcome some of the issues. So we'll see. So for those of you looking at geoimaging for the first time, this is actually something very similar to ultrasound imaging, but just in a very different kind of a frequency scale. So essentially what geoscientists is doing, something that I learned back in the time when I was at Los Alamos, they're injecting very low frequency wave into the Earth's body, and those waves will be propagating through the media and bounce back by some of the reflectors and eventually pick up by the surface receivers. And the way that they're presenting the data is intensive temporal versus the receivers, meaning that if you pick one single column out, that will be corresponding to the signal that is being recorded at a particular sensors. So that is the model we call the inversion net that was developed almost like 5-6 years ago. Now my thing's kind of straightforward, but back in the time, that was like the first types of machine learning models for solving seismic wave imaging problems. So I will still go through that because it really laid out a very good foundation for some of the latest and newest work that I'm going to introduce later. So two major notions here. The first one for inversion net, it tried to approximate it for a inversion operator, and two, it actually leveraging this image-to-image translation in an end-to-end manner, meaning that it takes the waveform data as an image and kind of output the speed of the sound of the velocity as another image. And it is trained in a fully supervised manner, meaning that you need to have the data and the velocity available at the same time. So to test it, this is one of the data sets that we actually generated and released to the public. We call it Open FWI, Open Full Waveform Inversion. It consists of a whole bunch of different distribution, and each type of distribution kind of representing a specific media complexity. So we have very simple kind of a velocity family, Veil family, to a Ford family, where we're injecting linear features into the media to model the heterogeneous velocity, which is actually much more complicated. And also we have some very kind of a specific domain relevant data set. So like I said, since inversion is a fully supervised method, you need to have the labels, which is the speed of sound, and you need to have the waveform data all together at the same time. And because there's not any physics domain knowledge being used, so you need to actually have a whole lot of data set in order to train these 20, 30 layers of CNN-based architecture. So we ended up using 60,000 of the velocity pairs just from one distribution to train the network. And this is coming from the Ford family, meaning that you have a linear features in the speed of sound. Now, looking at this in distribution test, actually, inversion net does a decent job. Since this is synthetic data, we actually have the ground truth, and we have the physics method, the one that I just telling you earlier, and this is machine learning, inversion net. I mean, that shouldn't look surprising to you because we all know, right? If you have sufficient amount of data, the neural network is going to be capture those distribution quite well. So What it becomes really challenging is when you're looking at out of distributions. Remember earlier we were saying, for all the training data set, there's a linear feature in it. If we're removing that linear feature and further apply inversion net, unfortunately, inversion net still feel like there should be some linear feature which really shouldn't be there. So that's where something we call it a very weak generalization ability regarding those purely data-driven models. All right, so this is where we were looking at, how can physics help, right? So we were talking about weak generalization ability as for those purely data-driven models. And unfortunately, this is a fully supervised method. Like I said, we have to have pairwise data. But for the problem domain that we're mostly looking at, no matter coming from geoscience or medical imaging, having pairwise, tens of thousands of pairwise data is usually very, very challenging. Not to mention that, due to this very deep structure of the network, the training cost is extremely high. All right, so how can we overcome those issues? So here comes the physics method that I'm going to introduce you. First thing first, what do we really mean by the physics in our notions here, right? So obviously, there are two parts of physics that I'm going to be talking about. So this is an animation kind of showing you how does the fluid propagated in a media. And the left panel here, this is how much of a fluid being propagating. And this is the spatial and temporal dynamics of the fluid. And the right-hand side panel, this is the waveform data. So obviously, wave physics, wave equation, it contains a lot of extremely rich physics behind that. So that's something that we should try to consider. And the other thing is the property of the solution space itself. So looking at this beautiful sound, obviously there are some high spatial frequency, as well as some very low spatial frequency here, representing the plume of the fluid. And those different frequencies of the spatial information contribute to the kinematics and the dynamics here as for the waveform. All right, so with my former colleagues in the lab, we actually come up with a review paper talking about how do we try to looking at both sides of the problems, physics and the data. This is actually a very hot topic, at least for our community. And we summarized that there are two major methods. One is built on the machine learning, and the other one is built on the physics models, and a whole bunch of different specific tools can be leveraged to combine information. I'm not going to go through details here, but for those of you who might be interested, please go through our paper here listed in the bottom. So this is one of the methods that I would like to introduce you. We call it influent, right? We published that about a couple of years ago in the ISML. And so again, going back to inversion net, right? This is something that I discussed earlier. End-to-end learning, a very deep network, fully supervised method. And one thing that is missing from this network is the physics, right? So this is where we keep asking ourselves. First of all, we are not just simply doing computer vision problems, doing this image-to-image translation. What we are doing here is actually, learning from one type of physical measurement and map it to another type of physical volumes. So that's where we actually using this network, we call it influent. From the high level, what it does here is actually to using kernel functions. To use those kernel functions, learning useful features first out of the waveform data and out of the velocity. And then we carry out a inversion in the latent space. And it turned out it actually saving you a whole lot of computation cost. But there are, of course, some advantage, and I will go through that. So the way that we do that, just going through some very kind of, high-level understanding of how do we try to deriving this influence. So using this 2D wave equation as examples, essentially what we're doing here is to separate the velocity away from the wave field, the waveform data, so that we can convert one to the others. And by further incorporate some Fourier series on top of the data, we actually obtain something on the bottom here. And obviously, the one on the right-hand side containing only wave fields, and that is straightforward to compute because we actually know the waveform measurement. What becomes really challenging related to the computation issues is the left-hand side, where it consists of a whole bunch of complicated terms to calculate. That's where we're assuming that the velocity on the boundary can be approximated by velocity across all the media. And this is a reasonable hypothesis due to the high coherence of the spatial velocity across all different depths here. And by further going through some linear algebra, we ended up getting a beautiful linear equations, right? So the linear equation was telling you by carry out some transformation, kernel transformation on top of the velocity and the waveform data, you actually having a almost linear equations. And how does that help related to our inversion? So that means, we can actually carry it out two nonlinear kernel transformation first, and that will give you a latent space related to the original waveform data and the corresponding velocity models. And the whole inverse problems can be solved and is embedding in the latent. And choosing the kernel, of course, can be challenging. But here, we actually having all these physics meaning behind the measurement there. So that's why in order to choose the kernel for the waveform, we ended up using Fourier sine or cosine. This is turned out to be a very good choice. Now, what it becomes challenging is actually the kernel as for the speed of the sound. So we tried a whole bunch, and in the end, we ended up using a general Gaussian kernel. It performs okay for some simpler velocity models, but when it gets to very complicated speed of the sound map, Gaussian kernel does not performing does not do a good job, and you will see what I'm saying later. But anyways, for now, let's stick with the Gaussian kernel. So here is the result. We have a speed of the sound ground truth. We have inversion net, the end-to-end purely data-driven models, and we have influent. This is built upon kernel, and we're doing the inversion on the latent, right? So just visually, influent performing quite well compared to the inversion net. And what is really impressive, due to the kernel functions here, actually the computation cost regarding the training has been significantly reduced. There's about 95% of a reduction as for the training cost. Now, what about more of a complex model? This is the one we have more of a kind of complex curve structure. Now, inversion that's still doing okay, but influent, like I mentioned, because of the poor kernel representation coming from the Gaussian kernel, it does not really capture enough information to carry out inversion in latent. So that's where we are thinking about, right? The couple of very interesting lessons that we learned. First of all, the kernel here is actually doing something very interesting. It actually kind of transforming the original nonlinear inverse problems into these high-dimensional latent space, and that becomes a linear inverse problem. So this is a very good lesson that we learned. And the other thing, selection of a kernel, like I mentioned earlier, is important. So for the work that I just telling you earlier, we're using explicit physical kernels. Well, for some typical wave functions, that's okay. But for some of the velocity models, physical kernel is not strong enough. This is where in one of our most recent work published in the SML recently, we actually brings back machine learning. That's where we were saying, rather than using explicit physical function as a kernels, here we actually using machine learning to capture, to learn those useful features, useful kernels, right? So in a high level, for this idea, it consists of two parts. The first one is two of the order encoder pairs to pick out useful features out of the waveform data and also out of the speed of sound. And the other thing, depending on are we looking at an inversion or are we looking at a full model, we will solving a linear system here to connecting these two kernels. All right, I will break it down here more. So like I said, the first part is a self-supervised training stage where we have a self-supervised on the waveform data, on the measurement, and we have another self-supervised pairs on the speed of a sound. And one thing I need to mention here, these two pairs of data, they don't need to be pairwise, meaning that you can just basically throw in as much of a data that you have regarding for this waveform, and at the same time, you can throw in, like the velocity model that you feel like it might be helpful into another pair of, autoencoder training. So these are completely self-supervised. So once we have these two pairs of autoencoder being trained, now you may want to ask yourself, are we going to be doing imaging inverse problems, or are we going to be doing form models, right? So this is more like a kind of a Lego games, right? For instance, when you're doing the inversion, what you could do is to using this encoder for the waveform and connect it with a linear operator, and then followed with a velocity decoder, and that's a inverse problems. Started from the waveform measurement, going through encoder and decoder, and solving the problems in the latent space that will give you velocity. Or you get almost for free the form model solvers. You can start it from the velocity decoder and follow with another linear problems here, and going through a waveform decoder, and that becomes a full problem solvers. Okay, So here is the result. And we have ground truth, the same example that I showed you earlier. Inversion-net, influence fail on this one, and ordered linear clearly give you better result. Now, regarding interdistribution, we compare all three models, inversion-net, influence, and ordered linear. They are comparable, good. Now, for out of distribution, influence is out of the pictures. So that's why I don't even put influence here. But ordered linear is actually giving you better result comparing to the in-distribution results from inversion-net. All right, as for the robustness test regarding noise, we have noise-free, low noise, and mediocre noise. And obviously for the ordered linear, which is plotted in blue, give you the most consistent results with respect to all different noise. Now, like I said, if you can solve inverse problems, you can solve four models at the same time. This is one of the demonstration. We have a velocity. This is the ground truth of the waveform coming out of a finite difference solver. And you have ordered linear, and the difference is here. So you can see ordered linear actually performing quite well to capture all the major wave phenomena here. All right, this is more of a complex finite difference result. And obviously, ordered linear give you a quite good result as for the full modeling. And one last thing that I need to tell you, for this ordered linearity, we demonstrate using wave equation, but it can actually extend it to other PDE problem as well. This is one of the demonstration using Maxwell equation. All right, so in the next few couple of minutes, I was just going through how do we using those models, but for very high frequency ultrasound data. So one thing that kind of we need to understand it is what is the difference in terms of a geoimaging versus ultrasound imaging. For geoimaging, we're using a whole bunch of geologically meaningful data as for the training data set. For medical imaging, we would need to have anatomically accurate phantoms as for the training data set. For geoimaging, we're usually looking at very large areas. The measurement could be quite sparse. For medical imaging, the measurement is actually quite dense, but the angle itself could be quite limited. Regarding the purpose, for geoimaging is mostly looking at structural information, but for medical imaging, you're looking at some fine scale with some specific tasks, such as detecting tumors or imaging the prostate, etc. So this is actually a very interesting work, thanks to our collaborators here from Johns Hopkins. We actually working together on these prostate imaging problems, and the most interesting thing for this application is that the data acquisition that we're looking at is quite limited. So as a rule of thumb, right, for most of the imaging problems that we've been looking at, we would like to make sure the aperture, how wide the imaging range versus the depth should be 5/1. That means you need to have a good data coverage regarding this, imaging domain. While for this one, it's actually reverse. It's like 2 versus 5. That's where you have extremely limited angle of the imaging domains. And we try to carry out our methods by first generating a whole bunch of data sets, and we ended up having around 5,000 and 4,500 is used for training, and the remaining is for testing. So this is the physics method. We have a ground truth. This is the numerical phantom, and we have a zooming region as for the prostate, and this is for the physics methods, ultrasound computed tomography. And you can see because of these very, very limited angles, the physics method does not really give you any meaningful information regarding the prostate regions. Well, this is the initial guess just to tell you where do we get started related to the iteration. As for machine learning, ground truth, and we have a different kind of a strategy to precondition the problem itself, but machine learning in general give you much better resolution, particularly related to the prostate regions. All right, so with that, I would like to conclude my talk by telling you a couple of lessons that we learned. And we started from inversion now, which is a kind of a purely data-driven models, and there's a lot of great potential out of that. But at the same time, we also realized that it has all these challenges in terms of high computation costs, weak generalization ability, heavy reliance on the labels, etc. This is where we bring in physics. We're using the kernel. We learn about these wonderful properties related to the linearity in the latent space. But at the same time, we learn the lessons that kernel itself physical kernel is not strong enough to actually carry out those learning. That's where we bring back machine learning to learn those kernel by itself, but we still keep the linearity. And as for the future work, as I show you, we would like to look at all different imaging modality, different applications. All right. So before I conclude, Together with my collaborator from Yale, we actually are going to kick out you probably heard about Kaggle. I know there's a lot of students here. We would like to have a Kaggle competition on this notion of computational imaging, and it's supposed to be happening very soon, but there might be some delay in terms of logistics, but yeah, keep your eyes on that, and hopefully that will be fun. And you can actually get money, right? So good. That's all. That's what I had to share, and thanks everyone.
So we're available for questions. Maybe I'll start off with an online question here. This question is from Tahir's iPhone. Can these methods be extended to incorporate wave physics described by stochastic or probabilistic equations, and not just deterministic PDEs? Yeah,
that's a good question. Yeah, the answer is yes. This is one thing actually in one of our most recent efforts. We have been looking at the diffusion model, and that was exactly as indicated by the questions. We would like to using some of the stochastic models to learn about the underlying physics, and so they can be used as a prior to constrain the inversion problem itself.
Great. So I have a question. So I don't know a lot about seismic imaging, but I noticed a lot of your kind of baseline ground truths have these almost piecewise constant homogeneous regions, right? And your estimates, and I don't know if it's the color map, but a lot of times the estimates look like there's kind of systematic biases to that. Is that important in seismic
It could be
imaging?
important. That's an excellent point. I mean, the reason why, for at least for geoscientists, they're always looking at the piecewise constant-based velocity model. Like I mentioned earlier, I mean, for geoscientists, they're mostly interested in the layer structures. They would like to know where is the layer, where is the reservoir shapes, things like that. As for the interior part, like the tomography part of the inversion, it may not be that much of importance. But that's one thing that we have to pay attention to when you're designing, for the regularization. Does it only emphasizing for the layer, or does it actually incorporating some of the heterogeneities within the velocity itself? So it is important. I mean, particularly for the ultrasound problems, right? That's actually quite important comparing to the geo applications there. Okay. Yes.
Very interesting talk.
Thank you.
I have a question, maybe naive. From what I understand, that you do the inversion in the latent space.
Yes.
Right? So I'm curious that that inversion is purely data-driven, or you also build in some physics inside that inversion? Because for a lot of us do medical imaging, we put a lot of physics modeling, physical knowledge in the forward process.
Right.
And at the end, we put that as a forward matrix, or system matrix, we call it.
Yes.
So when you do the inversion inside the latent space, basically, the latent space, the latent parameter has no physical meaning.
Great question.
And,
okay.
and when you do the inversion,
great question.
My guess is that you do like purely data-driven method. But can you also bring some physics inside that inversion?
That's a great, yes. This is something we are actually investigating right now. I mean, because we were also asking ourselves, right, from the computation perspective, sure, looking at this latent space, it much simplified this nonlinear inversion into a linear inversion. Now the question is there any physics being attached to the latent space? I mean, obviously, when you're looking at some of the wave theory, like the Born approximation, there are first order scattering, right, which is actually a approximation of the original wave equation. Is there any relationship in between these two? We are working on that. We haven't had an answer to it, but hopefully we can let you know soon.
Yeah,
Thanks.
We have some thought on that too. That's why I asked you the question, but we can talk more.
Sure, I'd love to. I'd love to hear your thoughts. Thanks.
Okay. Hey, thank you so much.
No, thanks everyone.